For my birthday recently, I was given a set of these. These are called egg weights, and they're made for exercise. These were given to me by my sister and brother-in-law, thank you, and it makes sense because I am a runner. They're very nice. They have these little loop-de-loops so you can put your finger through so you're not going to drop them as easily. And what you might not be able to see though is that these are quite dense. These feel quite heavy. This is actually 3 pounds of metal in my hands. This 3-pound weight set is apparently made of high-density stainless steel. And I want to put it to the test, and I want to know how high density this actually is. So I want to use these weights as an example of how to find the density of a sample that you don't know the density of ahead of time, and how to do it accurately so that you can get an A on your chem labs. Stainless steel is an alloy. Its main component is iron, which has a density of 7.87 grams per centimeter cubed when pure. But it's also mixed with some chromium, which has a slightly lower density, and small amounts of carbon, molybdenum, nickel, maybe even nitrogen, depending on the use that is being designed for. Several sources have told me that the density of stainless steel is typically between 7.5 and 8.0 grams per centimeter cubed, depending on the composition of the alloy. Alloys are mixtures. They're mixtures of typically metals, but sometimes nonmetals. And because atoms come in different sizes, we get 2 general categories of alloys. One is substitutional and one is interstitial. In a substitutional alloy, the atoms that are mixing are very nearly the same size. They're in the same range. When the new elements come in, they just simply take the place of one of the elements they're displacing. And since they're all about the same size, you get a basic substitution of an atom for another atom. In an interstitial alloy, there's this interstitial space between the atoms as they stack together. And if you put in a much smaller atom to the alloy, that much smaller atom can actually occupy the interstitial space between the big atoms, therefore limiting their movement, making the alloy a little bit stronger than the element would be by itself, and you have an interstitial alloy. So this is a combination of both. It is interstitial because it contains carbon, and those carbons limit the movement of the other atoms and hopefully making it stronger. And it's also substitutional because chromium atoms and iron atoms are of similar radius, so the chromiums can just swap out for an iron here or there. Stainless steels are typically above 10% chromium because it's the chromium that allows them to resist oxidation or corrosion. In order to find the density of these weights, I'm going to need to find their masses. So I'm using this scale right here, which is going to measure in kilograms, which then I can convert into grams. Let's put 1 on there. And I know that 1.5 pounds, which is what these are labeled to be, 1.5 pounds, is supposed to be 681 grams. This one happens to be 658 grams. And let's try the other one. And this one is 657 grams. So these are coming in a little less than 681 grams or 1.5 pounds, but perhaps that's to compensate for the rubber sleeve that was on those. Maybe with the rubber sleeves, they would get up to 681 grams. Just for fun, I'm gonna put one of these sleeves back on here. And now we're at 677, which is very close to 681 and very close to 1.5 pounds. So I guess that was, the weight of this was corrected for the weight of the sleeve as well. But here we have 657, which is 3 significant digits. I actually want to try to get 1 more digit of accuracy. So what I'd like to do is weigh both of them at the same time and treat them like one sample. So both of them put together are showing 1,315 grams, which is the total mass of both of my weights. Now that I know the masses of these to 4 significant digits, in order to find the density, I need to find the volume of these 2 together as well. And that poses a little bit of a problem because they're kind of an egg shape, as the label says. And it's not like I can easily measure the length and the width and the height of this thing to get a volume. So what we're going to do is something that you will probably be asked to do, and that is to figure out the volume using the water displacement method. The water displacement method goes something like this. You're going to start with a sample of water that you know the volume of to the best of your ability. And then you're going to add your irregularly shaped object to that water and watch the water level rise. And if you can keep track of how much the water level rises from the place that it started at, Then you can subtract to find the volume of your irregularly shaped objects. Whenever you take a measurement like this, you want to do it the best that you possibly can. And the first step in doing that is to look at your instrument to find out what it's measuring and what units and increments it's measuring in. This particular graduated cylinder is a 1,000 milliliter graduated cylinder. We can see the major lines are every 100 milliliters. And then there's 10 lines between them, so those would be the tens of milliliters. And there's no lines between that, so the limit of my device is to the tens of milliliters. So 500, 510, 520, and I can see I'm above 500, so I definitely do not want to put just 500 milliliters on there, because I know it's not. But it's not quite 510, according to my reading here. You're gonna have to get down low and look at it dead on if you're reading graduated cylinders. And I can see it's not quite 510. So should I put 510? Should I put 500? Or what should I put? A good measurement includes all digits given to you by your measuring device, plus one more, which is an estimate. Even if it's right on the zero, you're going to estimate another digit. So this went to the tens, and I wanted to go to the ones. So I can see that it's between 500 and 510. Let's estimate that. And I think it's really close to 510, so I'm just going to estimate 509 milliliters. That's what I wanted to do. So I estimated 509. And even if it was right on the 10, I would actually write down 510 and put that zero there. So as you're measuring along, make sure you note what place your instrument is giving you, and then go one more beyond that. Okay, so now I'm getting a little scared. I have a little problem because I need to get these heavy weights into my graduated cylinder, but the graduated cylinder is made of glass, and I'm really worried about dropping them in there because I feel like that's just going to be bad for the bottom of the graduated cylinder. So I think what I'm going to have to do is sort of do like a gentle addition, and this may be something you have to do if you're finding the density of rocks or something like that. What I'm going to do, wish me luck, is to put them in a little bit on the sideways and see if they will sort of gently work their way down. I'm just going to try to do this as super gently as possible. All right, let's get that down in there. Figure if I do it, oh, that was surprisingly hard, but I think our graduated cylinder is okay. We're gonna try this again with the second one. And don't wanna go too fast. And I also don't want it to overflow the edge of the graduated cylinder. And I think we have some success. I'm very excited about that. And my water level has definitely risen. We're well above 600. So let's take a moment and read that as best we possibly can. All right, we can see our stainless steel egg weights in there, and the volume level has risen. Now check this out. We're above 600, and we're gonna be above 650, which is right there. And that's 660, 670, and we're not at 680. So we're between 670 and 680. And I'm gonna say we're closer to 680 on that. So let's go with 678. How about 678? That's the best I can do. And some of you might disagree with me on that 8. You might think it's a 7 or a 9, depending on where you're at. But that's the nature of taking measurements. You have to estimate, and by nature, an estimate is just that, it's an estimate. But it is better than just saying 670 or 680. We're gonna go with 678. Okay, and now it is time to calculate the density of this stainless steel right here and see what it actually is, much in the same way as you will likely do in your chemistry labs. So follow along and do the same thing here, and we're going to be good. First things first, when you present your data, you're going to want to present it in a nice, orderly way and make it descriptive. Make sure you're putting down what it is you're measuring, as well as what substance you're measuring too. So yes, we're measuring mass, but we're also measuring mass of stainless steel. And we're measuring the volume, well, volume of what? Water. So you put that in there, make it nice and orderly, and you're going to put in your data to the best of your ability. Okay, so the first thing we're going to have to do, because density equals mass over volume, we need to find the volume of our actual samples. So let's add another line here. So volume of stainless steel. And that is going to be equal to, okay, that's going to be equal to, so volume stainless steel equals the difference between those two values. So the water level went up to 678 milliliters from 509. It's okay, you subtract them either way, but then just drop the negative because it does have a positive volume. And when I get that, I end up with a mass of a volume of 169 milliliters. Okay, so that's the volume of my stainless steel eggs. Okay, that's to the best of my ability according to my instrument. Okay, so the next thing, finding density, is basically, once you get to here, a one-step calculation. So we're going to say D equals M over V. Okay, and when you do calculations in chemistry lab, I always encourage my students, ask them to show me the formula that they're going to be using. Just write the blank formula so that anyone reading their work can say, oh, they're doing a density calculation. Then show the substitution, and then show the answer with appropriate units and appropriate sig digs. So since D equals M over V, I'll just draw a little arrow. We want to take the mass of our samples, 1,315 grams, okay? And we'll shorten that stainless steel. And we're going to divide it by the volume that we just found, 169 milliliters of stainless steel, okay? And I want to show you what my calculator gives me, because when I take those numbers and divide them, hopefully you can see that, 1315 divided by 169, my calculator gives me 7.78106508.9. Okay, and here's where we have to do a little judgment call. Okay, my calculator gave me like 9 or 10 digits. 10 digits. Okay, should I put them all? The answer is no, because I don't know them all. Okay, how can I know the answer to 10 digits if I only knew one of my measurements to 4 digits and the other one to 3? Those two are going to limit my answer, okay? And so the rule is, for adding, subtracting, you're going to limit your answer to the decimal place of the least accurate measurement. So if you had 1 to the tenths and 1 to the hundredths, you would limit it to the tenths. But here, when you're dividing and multiplying, you're going to count the number of digits in your measurements and limit your answer to the one with fewest digits. So 4 digits, 3 digits. That means my answer can only have 3 digits. And so my answer here is 7.7. And I want to make a judgment call, make sure I do it right. Now that 1 is just a 1. If that had been a 7 or an 8, I would round up the 8 to a 9 or something like that. But since it's not, I'm going to be keeping 7.78 grams per milliliter as my final answer. And maybe it's just me, but I like to put a little rectangle around my answer with a little heart next to it, because I just love when I get good answers, and I think that's a pretty good one. We've already learned that the density of iron is 7.87 grams per centimeter cubed from the periodic table. This is the accepted value that's listed there, and it's accepted value because the scientific community generally agrees on those 3 digits. There are actually theoretically more digits, many more digits beyond this. We just don't know them to any degree of accuracy, and so we don't include them on the periodic table. Density of stainless steel, because it's an alloy with varying compositions, generally falls between 7.5 and 8.0 grams per centimeter cubed. And the density of our egg weights, we just found out to be 7.78 grams per centimeter cubed. And the question we were asking is, if it's high density, how high density is it? So is this high density? Well, the value we found using our tools falls basically right in the middle of 7.5 to 8, right in the middle of the accepted range of stainless steel. So does that make it high density? Maybe not. I can be reasonably sure that it is stainless steel because it was advertised that way and my data support that. I can be reasonably sure that this weighs very nearly 3 pounds as advertised, which is great. But as for it being high density stainless steel, you can make your own decision about that as well. So there you have it. We found the density of our egg-shaped weights to 3 significant digits. If you've been following along, you learned how to take appropriate masses and volumes using a graduated cylinder or something like this. And you also learned how to carry your digits through the calculation and report your answer to the appropriate number of digits. Thank you for watching, and as always, if you have any questions, you can send them to me in the comments or directly. And in the meantime, happy studying and have a great day.